In our previous chapters, we studied the physics of stationary charges. So, in this chapter, we will study the physics of electric current, that is about the charges in motion. In electric currents abound and involve many professions. In meteorology, meteorologists are very much concerned about lightning and with the less flow of charge through the atmosphere. Biologists and physiologists are concerned about the nerve currents that control the muscles of the body. Similarly, electrical engineers are concerned with countless electrical systems like power system, lightning protection system, information systems, then music system. Space engineers monitor and study the flow of charged particles from our sun because that flow can wipe out telecommunication systems in orbit and disturb power transmission systems on the ground. So, almost every aspect of daily life now depends on information carried by the electric current, from stock market to ATM transfer, and from video entertainment to social networking. So, let's discuss the basic physics of electric currents and why they can be established in some materials and not established in other materials. So, what is current? Let's begin with the meaning of electric current. Current is any motion of charge from one region to another. In electrostatic, from electrostatic, you can say we came to know that the electric field is zero everywhere within the conductor, and there is no current. It doesn't mean that all the charges within the conductor are at rest. In an ordinary metal, such as copper, aluminium, few electrons are free to move within the conducting material. These electrons, free electrons, move randomly in all directions like the molecules of a gas with a speed of 10 raised to power 6 meter per second. These electrons cannot escape from the conducting material because they are attracted towards the positive ions of the material, and the motion of the electrons in conductor is random, so the net flow of charge in any direction uh, is zero. There is no net flow of charge, and of course there is no current. So now consider what happens when we apply a steady electric field inside a conductor. This is the case okay. So this is a conductor, and the charges are flowing in the conductor, or charges are here. Let's take a negative charge. This is the zoomed figure of this charge movement in the conductor. When electric field, we apply an electric field in the conductor, we know a charged particle is subjected to a steady force, F is equal to QE. Because we apply a steady electric field, so the force would be steady. If the charged particle moves in vacuum, then we know that this steady force caused steady acceleration in the direction of force, and after some time the charged particle would be moving in a direction at high speed. It will get accelerated. But a charged particle moving in a conductor undergoes frequent collisions with the massive stationary ions of the material. So here these conductor, there are also positive charges. and the ions are moving randomly in this electrons. Ions are fixed, and these electrons or the negative charge particles move randomly in the conductor. So this is a path of the charged particle moving in a conductor in a random way, in a random manner. Why it is random? Because a charged particle undergoes frequent collision with the massive ions of the material. So in each collision, the particle's direction of motion undergo a random change. The net effect of the electric field is that in addition to the random motion of the charged particle within the conductor, there is also a slow net motion or drift of the moving charged particle in the direction of the electric force. This motion is described in terms of drift velocity of the particles. So here, this green path is a random motion of the electrons without electric field. When an electric field is applied, so this green one is with electric field, and the red one, if you see this, the particle, the negative ion is moving without electric field from point P1 to point P2 again in a random way. So if you look carefully, when we applied an electric field, the path of the particle changes. It ends up at point P2 when there is no field, but when there is a field, it shifts from point P2 to P2 dash, and it covers some distance which is equal to Vt. So, and the other point to be noted is this, if you look here, when we applied electric field, the electric field is towards left hand side and the force is towards right hand side. The charge is moving opposite to the electric field. Here the motion of the charge is opposite to the direction of electric field. Let's suppose after some time this particle will reach towards point P3 dash, and it will continue until it will reach the desired point in the circuit.